In this lecture, we're going to talk about the different types of waves and the properties of waves. All right. So waves are consequences of oscillations. Things oscillate. Whenever things oscillate, they produce waves. Some examples that we meet in everyday life is, for example, waves on a rope. If you have ever gone to the gym, then may have seen this cardio rope where you hold on to one end of this rope and then make it go up and down, and you move back and forth, causing your heart rate to increase and hence causing you to have cardio exercise, right? When you move this rope up and down, you're actually oscillating, causing oscillations, and oscillations that result in waves along the rope. That's a very common examples of waves from everyday life. Another most important One of the most important experiences that we have is light. All light waves are light wave from the bulb in your room, or the light from the sun, the moon, etc. They can be considered light waves in very basic physics. I say that because it turns out that light is actually pretty weird. We don't yet know if light is completely a wave or a particle. We can't say for sure. But that's not the subject for today. Now, there are two types of waves that are classified on the basis of one thing: whether they require a material medium to do what we call the waving. For the wave to be there, do they need a material medium? If they do, then those waves are called mechanical waves. For example, the medium in this cardio rope exercise is the rope. Without the rope, you wouldn't see any wave, right? So this is an example of a mechanical wave. But there are waves like called electromagnetic waves that does not require any material medium. Examples of that include light or radio waves, or all of these things. They can travel through vacuum. Okay, they don't need a material like a rope or anything, air or water or not. So they can travel through anything. For example, they can travel through space. Light waves can be produced and seen in space. Okay, that's why these are called electromagnetic waves. Waves can also be classified on how they move from one point to another. In saying how they move means that to get from point A to a point B, they can follow two different methods of moving from A to B. One of the classification is that of a transverse wave. A transverse wave is a wave that has the oscillations causing the wave perpendicular to the motion or the velocity of the wave. So transverse wave have oscillations that is perpendicular to the velocity of the wave. The wave, if this is point A and that is point B, the oscillations in the wave can be seen to be going up and down at every point, right? And the velocity of the wave is getting from A to B, left to right. This oscillation is perpendicular to the velocity, hence we call this transverse wave. Examples of transverse wave are all electromagnetic waves and the waves you were producing in the cardio rope. Okay. Another classification is that of longitudinal waves. These are waves in which the direction of oscillation causing the wave is parallel to the velocity direction of the wave. So oscillations causing the wave is parallel to the wave speed, the direction of the velocity. Alright, so to get from point A to point B, all of the particles in this slinky is going in the rightward direction, and the oscillations in regions of compression and in regions of what we call expansions or rarefactions, we have the oscillations, right? So oscillations are either expanding out or contracting down, but regardless of the fact, regardless of compression or expansion, they're always parallel to the velocity of the wave movement. So these are longitudinal waves. The examples of longitudinal waves include sound waves, the waves on a slinky, which are produced by compressing and expanding the slinky, etc. Alright? Now, let's examine some properties that all waves share, regardless of whether they are mechanical, electromagnetic, transverse, or longitudinal, and so on and so forth. Wave properties include amplitude. In pink here, amplitude is the maximum displacement away from the equilibrium position. So this graph basically is, let's say, the wave you're producing on this cardio rope, and this graph shows you the wave at each point in space. Okay, so as it goes from the wall, let's say this is the wall, through to you. Okay, so this is the depiction of how the wave looks as it travels from the wall to you. The maximum displacement of the rope in the vertical direction is the amplitude of the wave you're producing. Okay, so that is the maximum displacement of from equilibrium position, and all waves have these properties. Amplitude is one of them. What is lambda? This Greek symbol lambda is known as the wavelength of the wave, and as its name suggests, it is basically how long the wave is. To know, to calculate or to understand how we measure the length of the wave, we either measure the crest to crest, so the highest point of waves is called a crest, the lowest point is a trough. So you can you can get one wavelength if you go from a crest to another crest, or if you go from one trough to another trough. Alright, so this is how you measure lambda of a wave. The frequency is denoted by f, as we have met before, and it is the number of complete waves per unit of time, and it is given by f equals 1 over the time period, capital T, as before. So how do we see this in the wave? Well, let's say in going from wall to you, in getting from this point to this point, I take a snapshot picture of a wave in one instant of time. Then the wave looks like this. So this is basically how the wave looks over time. Okay, so this is fixed in position. This is a wave fixed in position, but propagating in time. Alright, when you do that, then the time period would be the time taken to start repeating the motion. Okay, so either if you consider the crest to crest, when the wave goes from one crest to another crest, the wave starts repeating after the second crest, or once the wave gets from one trough to another trough, the wave starts repeating again. So this is the time period. Alright, this is how you see the time period on a wave. Now we also have the wave speed, denoted by v. This is basically, as again the name suggests, how fast the wave is getting from the wall to you, or getting from any 2 points, getting between any 2 points. And this depends on the medium through which the wave is traveling. So the rope will have a different speed because rope than waves traveling through water. All right, because water is a different medium than the rope, and it is defined by v equals f times lambda. So the speed is equal to frequency times lambda. All right, and what is frequency? Frequency is 1 over 10. So v is also equal to lambda over t once we replace frequency by 1 over t. All right, now let's look at an example and put all these into use. In this example, we have a string that goes over a pulley, and a mass or block hangs from it. Alright, the length of the string is as shown, 5 meter horizontal, 1 meter vertical, so the total length is 6 meters. L is equal to 6 meters of the string, and the mass of the string is 0.3 kilograms, while the mass of the block is 2 kilograms. And we are asked to find the speed of a pulse on this string. So if you move this block, if you release this block, then there would be oscillations in this string, right? Oscillations in the string would create waves, and we want to know what the speed of any pulse on this particular string would be. Alright, so as we have already mentioned, that speed or the wave speed depends on medium on which the wave is formed, right? And in this case, the medium is the rope or string, whatever you want to call it. Okay, it turns out that the speed produced on a rope or a string is given by this expression: V equals square root of Ft, which is the force of tension exerted by the rope, over mass of the spring or mass of the string or rope divided by the length or length of the string. All right, again, Ft is the tension exerted by the rope, Ms is the mass of string or rope, and L is length of the string. Okay, now it's time to go ahead and use this formula. Let's do that. What do we know? We know we want to find speed. We have the mass of the string, we have the length, so we have the mass and the length. What about tension? To find tension, since it's a force, we want to draw the free body diagram. On the free body diagram for the block, we have mg, the weight of the block, and then we have the tension force being exerted by the vertical rope. Since this is not in motion, it doesn't say that we are in motion, the acceleration is 0. And so the tension is actually just mg, the forces are balanced. And the mass of this block is 2 kilograms, so tension is 2 g newtons. Now we are free to use this expression, V equal to force of tension, which is 2 times 9.8, over mass of the string 0.3, over the length of the string, which is 6. Therefore, we find the speed. If you carry out the calculation, you find the speed of a pulse on this string to be 19.8 meters per second. Alright, this is how we work with speeds on a wave produced on a string. Alright, otherwise, if we were not specifically talking about this particular medium, we would be following the general formula for speed of a wave, V equals F lambda. And in future examples, we will look more closely at how to use this thing. Alright, I hope this lecture makes sense. Thank you very much.